Well, you may have seen this process done already, but I'm going to give you a video here that you can slow down if you need to and show the process of how we use integral calculus to calculate a moment of inertia for an extended object, something a little tougher than like a hoop or just a point mass. So we're going to do the rod or stick rotating about its middle, because I think that's probably one of the easier ones to grasp. Now, I apologize in advance for my crude drawings because I don't have my stylus with me, and yet I still want to make this. So here is a little picture of how the rotation is happening. I always show a little axis like that, and so we're spinning about the middle, and we're looking for the moment of inertia for this. So we're going to give this a mass of m and a length, the entire length we'll call L. That's very typical for a bar like this. And so the process starts by first imagining you have a very, very thin part of the stick here. And even though in the limiting case it doesn't really have any dimension, we're going to say it still has an infinitesimally small mass we'll call dm. And that mass is located a distance x away from the axis of rotation. And then we'll go to our fundamental equation that the moment of inertia is the sum of all the mr squareds. Now, a sum, when we do it in calculus, is written this way. And so the mr squareds, in this case, each m is a little dm, and each r squared we're going to write as x squared, because that's what that x means. How far from the axis is that little piece? So we just have to sum together all of those. Well, the toughest part of this is getting consistency in your variables. For example, you can't have a variable that looks like m here and a different variable that looks like x there. So the key is to write a proportion. And before we write the proportion, we have to describe how thick that little slice of mass is. And I can't really draw it with this resolution on the screen, but it has a thickness of dx. That would be if I could somehow measure the little thickness there. Well, if we consider how much mass that little slice is going to have, we would write this relationship. The amount of mass on the little slice is related to its thickness the same way the entire mass is related to its length. And so I can replace dm with an equivalent quantity m over L times dx. And so I'm going to take this whole quantity here, put it in my integral, and now I can write that I is the sum of all of the m over L dx, and of course I have the x squared that I had in the original relationship right above. I'm going to slide this up and give myself a little more room. Alright. Now, I'm just going to rewrite this. Now, if you're just now into integral calculus, you might not think to do this, although you've probably done it with derivatives. If something's not really a variable, I would not leave it inside a derivative or an integral. So I'm going to take out the m over L, and that cleans things up. And I also, it's bad form to write the dx first. You would typically write what we're going to refer to as the function, and then the dx. And now is a good time to put in what's described as the limits of the integral. So we're basically saying we've got different values of x, and that got a little messy. So what are the range of values that x can have? Remember, we measured x from the axis of rotation out to where our little slice of mass is. But our mass cannot go beyond the end of the stick. So the limits of our integral are between 0, that would be the piece that's right on the axis, all the way out to a distance of half the length. And so now we have an integral that we can actually do, and you'll recognize these. These will be considered easy in your calculus class. All right, giving myself a little more room now. Now again, if we just had this, what's on the screen now, someday in calculus you'll look at that and you'll say, oh good, finally an easy one. So here's how this works. M over L just goes along for the ride. And then we need to take the antiderivative. Oh, I'm sorry, that looks like a 6. That's a 0. The antiderivative of x squared. And I've described this for the newbies in calculus as, well, what function can you think of that has a derivative that is x squared? And you ought to recognize that as 1/3 x cubed. Now at that point, the integral sign goes away, the dx goes away, you've done the antiderivative. So we put our limits in. I always put them in right outside the brackets here. Not everybody uses brackets, but that's the way I was taught. And so now we have to plug in the upper and lower limit. And in this case, the L over 2, L over 2 gets cubed. So I'm going to just cube the L and cube the 2 separately. And then we would subtract it from 0 cubed, which is almost silly to write. But I'll write it just so those of you that are new to the calculus routine can recognize what we're doing. And so now I'm going to simplify a little bit. M over L. I have 1/3, and I have L cubed over 2 cubed, which is 8. So when I put the denominators all together, I get a 24. And the numerators all together, I get a ML cubed. So that's just one big fraction that can certainly be simplified now as 1/24 of ML squared. Notice one of those L's, this one here, will lower this by 1. Okay, and so what is that? That is the moment of inertia of the part of this where x ranges from 0 out to half of L. But that's only half of the stick. So I need to double this to account for the entire stick. So I might say this is just half of it, put a little subscript there. So the whole stick, kind of a goofy subscript, would be twice that much. 2 times whatever the half stick is, and that is the 1/12 ML squared, which is exactly what you're going to find on every chart or table, whether it's in our textbook or any other reference that you would use. So if you need to see part of this again, of course, the beauty of this is you can stop, rewind, and watch it again, but hopefully this helps us show one example of how integral calculus can be used to do something wonderful in physics, like find a moment of inertia.